All right. Hey, good morning, guys, or good afternoon. We are going to go ahead and start chapter 6 today. And chapter 6 is all about what are called systems of equations. All right. So a little different than what we've looked at before. But a system of equations, and we'll come back to this screen if you need to take a note on this for a second. But a system of equations is essentially this. All right, if you take a look at this top screen here, it says all solutions of an equation are on its graph. Okay, so any ordered pair that works in a linear equation could be thought of as points that make a graph. If we are going to look for a solution of a linear system, then basically what we need to do is we need to find a point that they share in common. Okay, and so what we're ultimately looking for, if you look at this picture off to the right hand side here, is the blue line, 2x minus 1, and the red line, negative x plus 5. Those two straight lines that are not parallel to each other and are not the same line will obviously intersect each other somewhere on the graph. And so that point of intersection is what we're looking for today. It's called the solution to the system. Okay, now there's three ways we can do this. We can graph it. We can look at a method called substitution. We can look at a method called elimination. I don't think I don't think graphing is always our best option, but it is probably our most visual option, and so that's why we're going to take a look at it today. We'll be focusing on this idea the remainder of the week, just looking at it in different directions. Okay, so as you see that picture there, that's what we're after today. Can we find that solution? All right, so I guess we don't need that screen, sorry. So if you have not, okay, you're going to label your notes today 6-1. Okay, we're starting chapter 6. We finished chapter 5 before Thanksgiving. Okay, so graphing systems of equations. We're only going to look at a couple of examples today. Okay, so we're going to take a look at, how do we find those solutions? How do we graph them? And then this idea right here about the possibility of solutions, this concept summary, you're going to need that as a part of your Google form for your homework tonight. So that'll be an important screen to make sure you pause on, either take a snapshot of it or copy it into your notebook. Okay, so we saw this screen, right? And ultimately, that's what we're looking for. We're trying to find that point where they intersect each other, because the order pair 2 and 3 is a solution to both the red equation and the blue equation. And obviously, if they're not parallel to each other, that only can happen one time. Okay, so that's something from chapter 5. No worries, we'll let that go for today. Okay, so our two goals for today. Number one, can we determine the number of solutions? Okay, so if those lines cross paths, that can only happen once. If they're parallel to each other, it can't happen at all. They'll never intersect each other. There'll be no order pairs in common, kind of like a no solution kind of idea. Or we might actually be looking at the same thing twice. And if we are, that's kind of like an infinite solution idea. So we have some names that get associated with those, and we'll talk about that more in a minute. Okay. And then can we solve systems by graphing, which is obviously what we're going to try to do. So as you see some of these words come across here, consistent or independent, dependent, inconsistent, that's a screen we'll get to. It's in your book as well, so you could find it there. I think it's on page 335, if I remember correctly. All right, so here's kind of our goal. Okay, so if we were going to graph this, we look at those two equations over there. They're not the same equation. Okay, they're not parallel to each other. If you recall, parallel lines have to have the same slope and different y-intercepts. So these lines are not parallel to each other, right? One of them has a slope of a half, the other one has a slope of 1. Okay, so our goal is to figure out what is that ordered pair they share in common. Code, what is the solution to this system? So if we were to kind of map this out, we'll let this top equation here be our red one. So if I was to graph that there, it would have a y-intercept of 0 and have a slope of 1/2. So up 1 and over 2, or maybe down 1 and to the left 2, somewhere along this path. Okay, so anywhere along here. I don't really know yet what the other one looks like. So for a moment, I'm just going to leave that kind of like that. And then let's switch over here and we'll graph this bottom one in blue. So it has a y-intercept of 3. All right, it has a slope of 1, right? I mean, there's nothing in front of that x, so really it's a 1 over a 1. So I could go up and to the right. That would be the path. But you notice here between the blue and the red, they're getting further away. So I'm actually going to go down and to the left. Okay, and as I continue down this path, that ordered pair right there is the line, or excuse me, is the point that both of these share in common. Right, there it is. It is the ordered pair 1, 2, 3, 4, 5, -6, -3. Okay, that ordered pair is the only ordered pair that those two equations share in common. Okay, so it is what is called their solution. If we plug this ordered pair into both the red and the blue, it would work for both. Obviously, any of the red dots or any of the blue dots would work individually, but that one works for both. Okay, so that's kind of our goal, and that's why we're looking at graphing today, because it's a clear visual of what we want. All right, there are two here. There's one here and one here. We're not going to do both of these. Just want to look at something maybe that's not necessarily solved for y. So, kind of thinking along those lines. We look at something a little bit different. So again, let's take this top one here and we'll solve that one. And if you don't recall, this one here is in what we call standard form. So we know it's a straight line. Okay, and maybe the best bet here is to solve this by its intercepts. So momentarily, I want you to think about, if I thought about this 3y not being there, kind of thought about it as y being a 0. If you solve that for x, divide both sides by 2, you would get x is equal to 6, which means it has an x-intercept of 1, 2, 3, 4, 5, 6. Has an ordered pair right there. And if I did the exact same thing over here, and I thought about solving it for y, you would see that it has a y value of 4. Okay, so it's got another ordered pair right there. Now that's only two ordered pairs, and the chances that I get a match is probably not too high. So what I could do here is kind of continue this by finding its slope. So you notice from point, the first one on the x-axis to the one on the y-axis, if I counted up 1, 2, 3, 4, and then to the left, 1, 2, 3, 4, 5, 6, I'll just mirror that. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So there's another ordered pair right there. So I am anywhere along that path. Now, if we come down here and we do the same thing for the blue one, if I just for a moment thought about getting rid of that y value, I would see that it has an x-intercept of 2. Dividing both sides by 2, I would get an x value of 2. If I slide that over there, that didn't work well for me, did it? It says -y. Let's take that back for a second. If we take this back over here and we just take that off, if we cover this one up, it says -y is equal to 4, which would mean y is equal to -4. So down 1, 2, 3, 4. Okay, I'm going to do the same thing here. You can see that the rise and run is up 4 and over 2. 1, 2, 3, 4, 1, 2. 1, 2, 3, 4, 1, 2. All right, and you can see now that our solution is going to be the ordered pair 1, 2, 3, comma 2. 3 units to the right, 2 units up. It is the ordered pair 3 and 2. So I don't necessarily always have to solve my equations for y. If they're in standard form, I can use their intercepts, and then I can mirror that and then extend their slope to do that as well. So two ideas here of how that works. All right, so we don't really need to look at this one. We could do the same idea there, or if we didn't want to, because we look at these numbers here, you have a y value of 3, an x value of 1, and then a c value of -2. That's not going to play very nicely for intercepts. So maybe you solve those for y. Move x to the other side, divide off the 3, get yourself a slope and a y-intercept. All right. Okay, so if you take a look here, it says here's this graphic summary of those possible solutions. You're going to need this tonight when you're looking at your Google form homework. But what we see here is that there are 3 different possibilities that could come into play for us when we're talking about graphing a solution to a system. What we've seen to this point so far is really this first option here. There's only one solution, and there's only one solution because these two lines cross paths at one point. Okay, what does that mean for us in a slope and intercept form, kind of down here at the bottom? Well, they have to have a different slope. All right, and they also have to have, well, we don't even have to say that. They really could have any y-intercept. Okay, the important part there is that their slopes are different. Now, if we jump down here to the last one over here, where it says no solution, okay, it's because our two lines are parallel to each other. If you recall, parallel lines, and we could, if we saw this, have to have the same slope, and they have to have a different y-intercept. Okay, so if you solved your two equations and you saw that they had the same slope, but they had different y-intercepts, well, then you got something going on there. And in this case, we see that we have parallel lines, which means there would never be a solution that they share in common. Okay, now the last one, which produces an infinite number of solutions, or what we would call consistent and dependent. This graphic is really the wrong color, to be honest with you. It shouldn't be a blue line, and it shouldn't be a red line. In fact, actually, this line should be purple. And hopefully you're saying because red and blue make purple, because we're really looking at the exact same line twice. And so they have the same slope and they have the same y-intercept. Now, if you're asking yourself, like, well, how could you not see that? Well, maybe, you had something. We'll just jump over here for a second. If I had two equations that were exactly the same, maybe the first one was y equals 3x plus 4. Okay. And maybe the next one said 6x minus 2y equals 8. Now, those don't look the same, but if you, and actually, they're not. Let's do this. Now they are. Okay. If you thought about solving this bottom one for y, you would notice that it's essentially just double everything that's in the top one. Meaning, if I was to add 6 to both sides, it would leave me with 6x plus 8, and divide everything by 2. I would end up with y is equal to 6 divided by 2 would give me 3x, 8 divided by 2 would give me 4. And all of a sudden now, I have the exact same equation twice, even though it didn't look like it was at the beginning. That would kind of be an example of this consistent and consistent and dependent, where we're producing an infinite number of solutions because every ordered pair is shared between both. Okay, so you're going to want to reference this screen when you're doing your homework today, tonight, this morning, this afternoon. I don't know, whenever you're going to get around to it. Okay, so consistent and independent is terminology that says, hey, one ordered pair that they share in common. That's it. Find it right there. What is its x and y value? Okay, consistent and dependent means that, hey, both these lines are exactly the same. There's an infinite number of possibilities that they share. And lastly, this idea of being inconsistent is kind of like saying, hey, we have no solution because these two lines are parallel to each other and they don't share anything in common. All right, last one, and then we're done. Take a look at this. I know you guys love words so much, right? So here in Canal Fulton, I think we got two things more than anything else: pizza places and churches. So I'm going to try to open up a pizza place. I'm going to try to get into the business, right? So it says we're going to open one up, trying to get some new business. I give you a promotional plan to become a VIP member. Everybody wants to be a VIP member. So you have two choices. You can pay me a monthly membership of $30, and you can get all the one topping pizzas you want for only $4 a piece, as many as you want. Doesn't matter how many in each day, doesn't matter how many in a month. Okay. Option number two, you can pay me $20 a month and you can get all your one topping pizzas for only $6. And again, you can get as many as you want. Okay. So my question is, at what point or at how many pizzas will both of these memberships have the same value? Because if your family's anything like mine, we order pizza at least twice a month, I would say. And so it wouldn't be hard to, buy a handful of pizzas if the price was right. Okay. So we're going to try to do that right now. Okay. We're going to try to figure this out, but we're going to do it in a graphical sense. Okay, so we're kind of thinking along these lines. Like, can I come up with some equation over here? Some y equals equation for one of them, and some y equals equation for the other one, where we can find this ordered pair right here that they share in common. Okay, so if we come back over here, option number one was to pay a $30 membership and you can get all the $4 pizzas you want. Okay, that $4 is that repeatable piece. So if we think about writing this, it's going to look something like this: 4x plus 30. Okay, now the other one, oops, let's go this way. Sorry, the other one was a $20 membership and you get all the pizzas for $6. So $6 is that repeatable piece. So here my slope is 6. Okay, so now we need to graph these. Now you can see I got total cost on my y-axis, because if you thought about spending $4 for a pizza and $30 for a membership, that result, that quote y value, would be your total cost. And my repeated x value in this case is how many pizzas that I'm going to choose to buy. So if I graph these two things to find that solution, the blue equation starts at 30. Okay, and it's going up by 4 every single time. So every pizza costs you $4. Now you got to be careful here, because your y values are counting by 5s and your x values are counting by 1s. So let's look for something that's like a solution that would be easy to graph. Like, for example, if I bought 5 pizzas, that would be a total of $20 additional. So 5 pizzas, starting here at 30, an additional $20 would put me about right there at $50. Okay, those 2 points would be enough for me to graph that equation, right? I could do what I did earlier with that idea of a slope. I counted up 1, 2, 3, 4, and over 1, 2, 3, 4, 5. 1, 2, 3, 4, 1, 2, 3, 4, 5. See how that works out to be the next order pair as well. Now, if I did the same thing with the red equation, starts at 20. Okay. And in this situation, there's $6 a piece. So if I did, if I bought 10 pizzas, that'd be an additional $60. So from 20, I'd be up to 80. So that's going to meet right there. That would be a second order pair. If I lay that out there, it looks like they're going to cross right there at that blue dot. Let's just make sure. That's up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So up 12 and over 10 would be the same as up 6, 1, 2, 3, 4, 5, 6, and over 1, 2, 3, 4, 5. And it is the same right there, which means that if you buy 5 pizzas, right, that's that number right there, 5 pizzas, and a grand total of $50, then both of these memberships are exactly the same. So are you a family that spends more than $50 a month on pizza? All right. Are you a family that spends less than $50 a month on pizza? Just think about that for a second. If you're a family like me, okay, I probably spend more than $50 a month on pizza. Which membership is a better deal for me? At $50, they're exactly the same. You can see it on the graph. They match. But what if I spend more? Am I better off with the red equation, or am I better off with the blue equation? Stop for a second and think about that. I buy more than 5 pizzas in a month. Which one is better for me? Okay, hopefully you're going to say the blue equation. If you look at the blue one, once we pass this break-even point, it's lower than the red one. And since the blue one is lower than the red one, it has a lower overall price. If you're somebody that spends less than $50 a month, then we're looking to the left of that dot, and we can see there that the red one is actually lower than the blue one, so the red one's cheaper. Okay, so in a system, we're looking for that point that they share in common. All right, their solution to the equation. If you have any questions, don't be afraid to stop in and ask. All right, your homework tonight is going to be a Google form going over this idea. It is going to be very important that you remember this slide while you're working on your homework tonight. Message me if you have any questions. Bye.